आइए हम सुने विज्ञान की अनकही कहानियाँ। आइए हम सुने विज्ञान की अनसुनी कहानियाँ। एक नई दुनिया की आवाज आपकी आवाज, विज्ञान की आवाज, की आवाज।
Celebrating Azadi Ka Amrit Mahotsav, we bring you a podcast series on STEM popularization, science, technology, engineering, mathematics and medicine, supported and catalyzed by the National Council for Science and Technology Communication, Government of India. This program is produced by Media for Community Foundation. Creative content and technical support is given by Salam Namaste Community Radio, Noida.
एक नई दुनिया की आवाज आपकी आवाज, विज्ञान की आवाज, की आवाज, की आवाज।
आज की प्रमुख स्टेम पॉपुलराइजेशन जानकारियाँ।
विज्ञान के दुनिया से आज की जानकारियां।
गगनयान मिशन 2035 तक भारत का होगा अपना अंतरिक्ष स्टेशन, इसरो चीफ ने दी अहम जानकारी। मनोरमा ईयर बुक 2024 किताब के एक लेख में इसरो चीफ एस सोमनाथ ने कई जानकारियां दी हैं। उन्होंने बताया कि भारतीय अंतरिक्ष स्टेशन 2035 तक चालू किया जा सकेगा। इसके बाद 2040 में गगनयान मिशन की सफलता पर चांद पर पहुंचेंगे भारतीय अंतरिक्ष यात्री। चंद्रयान 3 के ऐतिहासिक सफलता के बाद दुनिया भर की नजरें इंडियन स्पेस रिसर्च ऑर्गेनाइजेशन पर टिकी हुई हैं। इसरो के वैज्ञानिक अब तक के सबसे कॉम्प्लेक्स टास्क गगनयान को सफल बनाने के लिए खूब लगन से काम कर रहे हैं। आपको बता दें कि गगनयान इसरो का अब तक का सबसे बड़ा और चैलेंजिंग मिशन है। इस मिशन में न सिर्फ भारतीय अंतरिक्ष यात्री को चांद पर पहुंचा सकेंगे, बल्कि वहां कुछ दिनों तक समय बिताकर सुरक्षित वापस भी आएंगे। मनोरमा ईयर बुक 2024 किताब के एक लेख में इसरो चीफ एस सोमनाथ ने लिखा है कि इसरो का लक्ष्य गगनयान कार्यक्रम के साथ अंतरिक्ष अन्वेषण में अगला कदम उठाना है, जिसमें 2 से 3 भारतीय अंतरिक्ष यात्रियों के एक दल को 3 दिन तक पृथ्वी की कक्षा में भेजने की योजना है, जिसके बाद उन्हें भारतीय जल क्षेत्र में पूर्व निर्धारित जगह पर सुरक्षित रूप से उतारा जाएगा। विज्ञान की दुनिया से आज की अहम जानकारी। जापान ने क्रिएट किया कुछ ऐसा फ्यूजन, सूरज की तरह पैदा होगी एनर्जी। दुनिया में आज की तारीख में न्यूक्लियर फिजन पर एटॉमिक रिएक्टर से ऊर्जा उत्पादन किया जा रहा है, लेकिन जापान के नाकानार्थ में JD60SO न्यूक्लियर फ्यूजन पर काम कर रहा है। इसके जरिए सूरज की तरह ऊर्जा पैदा की जाएगी। न्यूक्लियर फ्यूजन में हाइड्रोजन के 2 परमाणु आपस में मिलकर हीलियम बनाते हैं और उस प्रक्रिया में असीमित ऊर्जा निकलती है। दुनिया के सभी मुल्क इस बात को लेकर चिंतित हैं कि ऊर्जा की जरूरतें कैसे पूरी होंगी। बिजली आज हम सभी की जिंदगी का अहम हिस्सा है। बिजली पैदा करने के लिए कई तरीके हैं, जिनमें न्यूक्लियर रिएक्टर भी शामिल है। दुनिया के विकसित देशों में न्यूक्लियर रिएक्टर के जरिए बिजली पैदा करने पर काम दशकों से चल रहा है। इन सबके बीच जापान के नाका नॉर्थ में दुनिया के सबसे बड़े न्यूक्लियर प्लांट ने काम करना शुरू कर दिया है। यह एटॉमिक प्लांट क्यों खास है, इसे जानना भी बेहद जरूरी है। नाका नॉर्थ में स्थापित इस न्यूक्लियर रिएक्टर का नाम JT60SO है। इसमें सूरज की तरह ऊर्जा पैदा की जा रही है। अब यह दुनिया के दूसरे प्लांट से अलग क्यों है? दरअसल अभी तक जितने भी न्यूक्लियर रिएक्टर काम कर रहे हैं वो न्यूक्लियर फिजन पर आधारित हैं। इसका अर्थ है कि एटम के विखंडन से ऊर्जा पैदा की जाती है, लेकिन JT60SO न्यूक्लियर फ्यूजन पर काम कर रहा है। इसका अर्थ है कि हाइड्रोजन के 2 परमाणु को जोड़ने से ऊर्जा का उत्पादन होगा। बता दें कि अभी व्यावसायिक स्तर पर ऊर्जा का उत्पादन नहीं किया जा रहा, अभी केवल ट्रायल किया जा रहा है। अगर कामयाबी मिली तो यह कार्बन मुक्त ऊर्जा हासिल करने का बेहतरीन स्रोत होगा, जिससे प्रदूषण पर लगाम लगाने में मदद मिलेगी।
STEM एम्पलीफायर।
आज के हमारे विशेष अतिथि हैं डॉक्टर अभी दे सरकार। ये वर्तमान में भारतीय नैनो विज्ञान एवं प्रौद्योगिकी संस्थान मोहाली में साइंटिस्ट F एवं डीन फैकल्टी के पद पर कार्यरत हैं। उनका वर्तमान अनुसंधान क्षेत्र है साइंटिफिक कंप्यूटिंग एवं कंप्यूटेशनल नैनो साइंसेस।
So I'm into scientific computing. I pursue research in the broad area of computational nanosciences in the realm of computational nanosciences. We employ density functional theory based approaches for the pursuit of our scientific research. Apart from the independent pursuit of our research in this domain, we do collaborate with experimentalists and provide them with theoretical support. And my major thrust area is two-dimensional materials. So flat materials, ultra thin flat materials. So you may be aware of graphene. The discovery of graphene was already a revolutionary step in the history of science, and for which it was awarded the Nobel Prize in the year 2010. But graphene, there are some pristine graphene has certain limitations. It doesn't have a band gap, therefore it cannot be used in several applications such as electronics. So therefore alternatives to graphene have been sought after. So two-dimensional materials, what I mean to say is that flat materials which are ultra thin, so these are usually multi-layered solids, and it can be peeled off by a scotch tape or by several other experimental methods. And when it is thinned down to the level of a single layer, novel properties arise. So novel properties arise at the nanoscale, which are usually non-existent in the bulk form of these materials. So molybdenum disulfide happens to be the most widely studied semiconducting two-dimensional material. So we have also done a good deal of work on this material and several other two-dimensional materials. In the past, I have conducted research on computational catalysis. During my PhD days, that was my main research area, and even in my first postdoctoral stint at the Fritz Haber Institute of the Max Planck Society, Berlin, there also I had continued working in the area of catalysis. And then I gradually drifted to surface science and catalysis. And finally, here when I have started my independent career, when I have joined here in 2014, I have been pursuing area on two-dimensional materials for different kinds of energy conversion and next generation electronics. So in terms of science, India is at par with the rest of the world. So National Supercomputing Mission of the Government of India, it has been supporting researchers strongly across India. We have access to the supercomputing resources. We have built in-house supercomputing facilities in different institutes in India. So in terms of facilities, we have robust computing facilities, and the level of science which we are delivering, that is comparable to the rest of the world. Right. But in terms of technology, probably we are lagging behind a bit, because still we need to import the chips from Taiwan and so on. But in terms of science, we are at par. We are not lagging behind in any terms, in terms of publications, in terms of ranking and so on. I have published more than 100 papers in scientific international journals. The initiative is not as strong as it is in the West, in Netherlands or in Germany or in US or in other parts of the world. Here, initiative has to be a bit stronger. Like I mentioned to you, novel properties arise at the nanoscale, which are usually non-existent in the bulk form of these. Let us consider this a layered solid like molybdenum disulfide, as I mentioned, and when it is thinned down to the level of a single layer, interesting properties arise, such as piezoelectricity, where the inversion symmetry is broken. So what is the inversion symmetry? Is like this. If I look into myself in the mirror, I'll see an image of myself. And now if you replace me by an atom, so say for example, I look into the mirror, I do not find myself in the mirror. I do not find an image of myself in the mirror. I find a stranger in the mirror. Okay. So then we say the mirror symmetry is broken, or the inversion symmetry is broken. Now suppose you replace me by an atom. Suppose it's a carbon atom looking into the mirror, and it doesn't find an image of itself in the mirror. It finds another atom. Say it finds nitrogen in the mirror. So boron is on this side of the mirror, and on the other side of the mirror the image is that of nitrogen. So in that case the inversion symmetry is broken, and as a result of which piezoelectricity arises. And this is a relatively new finding, and there is immense scope for this. This is an emerging field of research, and there is immense scope for development of this research area for an understanding as well as incorporation of this additional functionality into devices. So we have contributed a bit in this direction through our studies on, say, heterostructures. So one two-dimensional material interfacing the other two-dimensional material, how the two materials, they are talking to each other. At the interface, some piezoelectric effect is generated. So, and a high level of piezoelectricity which is generated at the interface, that can be utilized in several applications. Like for example in next generation electronics. Suppose even in case of charge transport, suppose current is flowing through a device, and now electron has several properties, like it has a spin degree of freedom also, which can be utilized in transmitting information from one place to the other. So even to transmit information from one place to the other, this piezoelectricity would be helpful, because there is a piezo potential, say generation of electricity or voltage upon the application of pressure. So through that out of plane piezoelectric potential, so through the piezo potential, one can control the transmission of information from one place to the other. So this spin degrees of freedom can be used to encode, store and process information, and how the information will be processed or transmitted from one place to the other, that can also be controlled by this piezoelectricity, and it doesn't require any external voltage or a power source, because it is self-powered. Just by applying mechanical pressure, the electricity or the voltage can be generated. So that's the advantage of piezoelectricity. And so piezoelectricity, mankind can benefit immensely from the applications of piezoelectricity. Say for example, piezoelectric nano generator. Say if you have a piezoelectric polymer, then that can be used in the pacemaker. Now the pacemaker is usually operated by a battery. If you can make it battery less, if the piezoelectric material can obviate the need for the battery, if you do not need the battery, then that will be substantially beneficial. Then through the motions of the body, you see the biological rhythms, the biological motions are very rhythmic. Through the bodily motions, the piezo potential or the voltage can be generated, and that can potentially replace the battery, and that will be quite revolutionary in the history. That will be a very revolutionary thing to do. Yeah, it will significantly advance both the science and the technology. Now the science is kind of very well understood. Now how to translate this into a technology? There can be several technological hassles and challenges here, because how you contact this material, the contacts, how it is forming with the other materials, that is contact properties, there can be a challenge. So during my PhD days as well as in my first postdoctoral stint in Berlin at the Fritz Haber Institute, I was simulating the catalytic reactions, the reactions which take place at the catalytic converters of the automobiles, with carbon oxidation, then nitric oxide reduction. So some targets have to be met, have to be reached. I mean, the whatever is coming out of the exhaust of the car, so that has to be minimized. So some stringent regulations were there from the European Union as well as from US. So we were working, I was pursuing research in that direction, so that we choose an appropriate catalyst so that it will reduce the pollution. So to bring down the level of pollution, because cars pollute the environment, how can we bring down the level of pollution? So that was my main research area at that point of time. And then it was then simulating, calculating the images, STM images. How does a molecule look under a scanning tunneling microscopy, and how can we design molecular gears? So nano cars, if we have to run nano cars, that also I was working under the supervision of Professor Christian Joachim of CNRS France. So yeah, there I had also collaborated with experimentalists and provided them with theoretical support. So the thing is that, the youngster should should consider a career in scientific research seriously. So in computational material science, there's immense scope and prospect in this research area, because it will save the time of the experimentalists tremendously. Whatever we make theoretical predictions in the lab, because the level of theory which we use is density functional theory, which has been awarded the Nobel Prize. The level of accuracy is extremely high, is exceptionally high. So therefore people, youngsters should seriously consider pursuing a career in this direction, the direction of computational material science. The job prospects are
STEM बात पते की।
अब जानते हैं पृथ्वी गतिशील है, फिर पता क्यों नहीं चलता? हमारी पृथ्वी लगातार अपनी धुरी पर घूमती रहती है। ऐसा नहीं है कि हमें पृथ्वी की गति का पता नहीं लगता। दिन में सूर्य की बदलती हुई स्थिति से हमें पृथ्वी की गति का आभास होता है। पृथ्वी का घूमना हमें महसूस इसलिए नहीं होता क्योंकि पृथ्वी बराबर एक ही गति से घूम रही है। किसी भी वस्तु की गति का पता उसकी गति में आने वाले परिवर्तन से होता है। पृथ्वी की गति में परिवर्तन न होने के कारण ही हमें इसके बारे में पता नहीं चल पाता। साथ ही हमारा अस्तित्व भी पृथ्वी की तुलना में कण मात्रा से कम है।
ये था आज का विज्ञान की आवाज। आपको ये पॉडकास्ट कैसा लगा हमें बताएं mediaforcommunity@gmail.com पर।
आइए हम सुने विज्ञान की अनकही कहानियाँ। आइए हम सुने विज्ञान की अनसुनी कहानियाँ। एक नई दुनिया की आवाज आपकी आवाज, विज्ञान की आवाज, की आवाज।
Celebrating Azadi Ka Amrit Mahotsav, we bring you a podcast series on STEM popularization, science, technology, engineering, mathematics and medicine, supported and catalyzed by the National Council for Science and Technology Communication, Government of India. This program is produced by Media for Community Foundation. Creative content and technical support is given by Salam Namaste, Community Radio, Noida.
एक नई दुनिया की आवाज आपकी आवाज।